Hello and welcome. This is a problem about a closed process. A gas trapped in this piston cylinder device, a closed system, undergoes an expansion. It's heated by an external source, and the initial state, the begin state, everything is given 1 kg of air at this condition, and it's a constant pressure process. That is, the pressure inside the chamber doesn't change, as can be obvious from the free body diagram of the piston. The final temperature is supplied to us, and we are asked to find the heat transfer and the boundary work. We'll also find the entropy generation if possible, and we might try to do a parametric study. What if the final temperature is not 1000 Kelvin, but say 1500 Kelvin? How would that impact the answers? So let's begin. I have already logged in as a student. We'll find a suitable test step. Obviously, this is a closed system, so we'll follow the system analysis closed path, and it's a closed process, generic system. So this would be our destination in our progressive simplification scheme. And the model to use, we'll use a gas model. The PG model is the simplest one. And finally, go to the HTML5 page to launch the test app. Okay. So it's assumed that you're familiar with evaluating state using any of the system state using different kind of test apps. Okay, so let's begin. The initial state, what is given to us, is supplied here. Okay, so air is already the selected fluid by default. State 1 is our beginning state. Let's evaluate the state. The information supplied are temperature and pressure and the mass. Once the state is calculated for state 2, we know it's a constant pressure process equals P1, and mass must be same as M1. But instead of supplying the temperature here, we'll go to the I/O panel, isolate user codes, and declare a final temperature, T final equal 1000. This way we can do a parametric study. Notice that I declared the variable as T final, not T2, because that's a reserved variable. So I click enter or calculate to register the value. So the final temperature can be seen as 1000 Kelvin. We come back to the state panel, and instead of using 1000 Kelvin, we'll say equals T final. The beauty of this is later we can just go and change T final and see its effect. Just to make sure we got the right value, if you park the pointer on T final, its value should show up right about here. So that's the top help panel. Okay, so that the state has been evaluated. Notice that even the picture of the state changes as the temperature changes. Okay, now that the beginning and final states have been calculated, we go to the process panel. And there we are going to analyze the process with the help of this mass, energy, and entropy equations. Okay, notice that the energy equation requires us to input either Q, boundary work, or other kind of work, etc. The WO is nothing but shaft and electrical work combined together. So keeping that in mind, we know there is no shaft and electrical work, so it's already set to 0. And we don't know what the boundary work is, neither do we know what is the heat transfer. Let's give it a shot if the test step can figure this out. So what we do is simply load state 1 as our initial or beginning state and state 2 as our final state and try to calculate. And notice that the boundary work is automatically calculated because the app knows it's a constant pressure process, and therefore it can calculate boundary work. And once the boundary work is evaluated, it can evaluate Q from this energy equation. But what a surprise. So the entropy generation is negative, which is impossible. That's the reason is that in this case, we're heating the system from a beginning temperature of 300 to 1000 Kelvin. So the boundary temperature cannot be, look, by the default boundary temperature is only 298 Kelvin. That's why entropy generation turned out to be negative, telling us that something is wrong in our boundary temperature. So suppose in this problem the boundary temperature is supplied, that Let's say the candle temperature was 2000 Kelvin. That was supplying the heat. In that case, notice the entropy generation will turn positive. Of course, the answer will depend on what the boundary temperature is, which is not given in this problem. But it's interesting to note that the negative value of Sgen signifies something impossible, and it's always a good idea to look for a physical explanation for that. Well, the last thing, so we found the heat transfer, so let's make a note of that. So the heat transfer is 702 and the boundary work is 200. So let's go and just repeat the calculation for a different final temperature. Let's say we say the final temperature is 1500 Kelvin. And you'll see how easy it is now, the way we set up the problem. So the temperature has been registered, 1500 Kelvin. And all we need to do is to click the Super Calculate button, and all calculations are updated. If you come to the process panel, look, it is 1204 now, 344 now, as opposed to 702, etc. And 200, I believe, was W external.